So hi everyone, welcome to our first solar eclipse QSO party for the 2023-2024 series solar eclipse QSO party telecon. We're going to have this weekly from now for the hopefully next few years, and hopefully we're going to create a really fun ham radio operating event and hopefully get some good science out of this. So today our primary event today is going to be hearing from Frank Howell, who I will introduce in a second. And then the other thing I want to do is just kind of give you a brief outline of where we're going to be going in the next few weeks. I think next week what I'll do is I will give a recap of what happened during the 2017 solar eclipse QSO party, so we can just revisit that. And then I'd like to introduce Gary AF8A. He's online here. He is a member of our GRAPE group, the GRAPE Personal Space Weather Station group, and he has also volunteered to be our amateur radio coordinator for the solar eclipse QSO party. So anything that deals with the amateur radio side of the planning, the contest sort of event, Gary's going to be in charge of that. And then myself, I'm an assistant professor here at the University of Scranton, and my colleague on here, Gareth, where are you, Gareth? Gareth Perry is an assistant professor over at New Jersey Institute of Technology. We're going to take the lead on guiding the science part of it. And hopefully we'll come up with a really fun, productive thing.
So sorry, Nathaniel, here I am.
Hi, Gareth, how are you?
I was unmuted.
That's better.
I'm well.
I just want to introduce you to everyone. Gareth is KD2SAK, and he is my colleague at the New Jersey Institute of Technology. So we're going to work together on guiding the science portion of this. And I think that's it for now. And later we will have a chance for everyone to introduce themselves as well. But without further ado, why don't we get going with the presentation part of this, and we're going to hear from Dr. Frank Howell, K4FMH, and he is going to present a seminar based on his two-part article, which was published in the July and August 2022 issue of the Radio Society of Great Britain's RADCOM. And this was written with Dr. Scott McIntosh of the National Center for Atmospheric Research, or NCAR, out in Colorado. And this is titled "On the Cusp of the Scientific Revolution." So,
hey,
yes.
Nathaniel, you
Yes.
might remind everybody to mute so that there won't be a lot of interruptions during the presentation.
Thank you very much, Ron. Yes, I will remind everyone to mute. And in fact, I'll go a step further. I will mute everyone at the beginning. And you will be able to unmute yourself if you need to. And I'm going to make Frank.
Yeah, so I can post the PDFs in the chat. I have to be co-host, I think.
Oh, okay, great. So you are now co-host.
Speech mode speaks. Speech mode talk.
Everyone is muted. So Frank, you can go ahead and unmute yourself, and then go ahead and take it away.
Okay, thank you, Nathaniel, for that. Just a FYI, I still don't see an ability for me to load a file in chat. I do that on Saturday mornings in the Cycle 25 group. Nathaniel, I have sent you those. If you would post them in the chat, you certainly have my permission to do so.
Great.
Listen, thanks everybody. I don't know if Scott McIntosh will be able to make it or not. He also has an administrative appointment over their air flight system, so he's certainly been quite busy. A lot of impressive names here today. I'm very honored for anyone to volunteer to spend time to listen to me talk. I consider time the most precious commodity, so I take that with gratitude. Nathaniel, I need you just to verify if you can see my PowerPoint.
I can see it.
All right, I do have sound in one part of it, so I hope that works.
Yeah, you just have to make sure you click share sound.
Yeah,
Then
I have done that, and it shows the little button there. So very good. The title of this talk today is Revolutionary Alternatives in Sunspot Prediction. And it's based upon an article in Radcom. It was reviewed by their RSGB propagation committee, and as the Brits would say, such a controversy. Certainly, anytime you have some ideas that go against the grain of what's established, it technically is controversial. I would wager that is a fair statement today. A year from now, it may not be. So Dr. McIntosh is a leading solar physicist, as Nathaniel said, out at NCAR. I'm professor emeritus at Mississippi State and adjunct professor at Emory. I'm not a solar physicist. Let me wave my arms. If there was a wave my arm emoji, I would use that now. I am a sociologist, statistician, and philosopher of science. I've taught those subjects to PhD students and other faculty for a number of decades. Been a consultant to federal agencies on grant awards and peer review processes. And you might think, gee, why is that? Well, often peer review grant processes aren't fair. I know it's a shocker to some of you who served on panels, but they don't play fair necessarily because they tend to come at it from their paradigm. And so agencies like NSF, NIH, and USDA have been concerned to make sure they're not missing people by virtue of who they have on these review panels. So I've done some work there. I interviewed Scott in 2020 on the ICQ podcast, which I've been on off and on for about 12 years now, and I got to know him, and we become good friends and colleagues, and it's just quite an honor for me to work with him. The meat and potatoes of the Radcom articles came from Scott and his team. My contributions were to help them get some of their earlier work published by dealing with reviewers and this issue of paradigm conflict and how to get by peer reviewers who kind of weren't necessarily playing fair or who were holding higher standards that they themselves don't adhere to when they publish. And so also help with some of the statistical basis of what they've been doing. Here are the covers of the two articles in Radcom. And if Nathaniel's successful, I'm putting those out there. I'm claiming fair use exemption under copyright law here in the US. I know that Elaine Richards, the editor, won't have any problems, with that. She is transitioning into retirement. I've got a little summary of bullet points on the right-hand side of the screen. I want to apologize to you if this gets deep, because it will. It's a nuanced argument. It's going to run 30 to 45 minutes, and I'll try to interject humor where it's appropriate. I always think that kind of keeps an audience awake and focused and that sort of thing. So we'll entertain questions hopefully at the end, unless there's just a really big one that you need. Where are we today? What about sunspot occurrence? What are the official predictions of cycle 25, and what are the competing predictions? Well, here's a graph that many of you may have seen. I want to focus your eyes on this black line. These are the observed smooth sunspot counts up here to what was posted in August, which would probably be in the end of July. And as I have said on Twitter, they're right on to the bone. I'll explain that in a minute. Let me point out in the beginning, you see all these light green lines going up and down. I got grants, bought big computers back when a Sun 690 multiprocessor was considered a big computer, like a walk-in freezer, solely for the purpose of doing data visualization and developing tools for data viz. I worked with a group up in Piscataway, what used to be called Bell Labs, and a number of scientists and professors in data viz. I want to point this to your attention. We often look at the smooth sunspot. I don't think our ionosphere has ever been affected or influenced by a smooth sunspot. That's for human consumption. These jagged lines that go up and down are what really affect the ionosphere. Very often we see a smooth sunspot, and one person would say, oh, the bands are crap, they're not doing anything. Well, that smooth sunspot might be at 85 or so, but the actual sunspot for that day might be down in the 20s. And same thing vice versa. So the smooth sunspot, here you go. Let's look at the official predictions. You've got two for NASA, NOAA, the lighter blue, which was their earlier prediction, and then their adjusted prediction here. So this is what the official predictions happen to be. The dark green is simply if you take the average smooth sunspot number for the solar cycle since 1750 and just project out the average, kind of like betting the average in the stock market, this is what you'd see. So you see the official predictions seem to really be different for what's been statistically true since the first solar cycle. Well, we all know averages lie. I try to stay out of bathtubs that average a depth of 3 inches. I heard a statistician drown one time in a bathtub like that. The Macintosh, Lehman, and others team, their predictions are in red. As you can see, they're quite distinct and different from the official predictions. Thus far, as I said, they're right on to the bone. Well, why is this important? Well, the reason is we need to think about what we think about sunspots. We take a lot of that for granted, even though we pay a great deal of attention to sunspot cycles in amateur radio. We are loyal to that paradigm of a sine wave, even in the face of many anomalies. The famous little web widget here on the right, I used to have it on my website at k4fmh.com, and for some reason I changed some things and it got broken and I sort of took it off. It's ubiquitous anyway. I liken sunspot or propagation indices are like the Dow Jones Industrial Index. If you're an economist or a financial investor, you live, eat, and breathe those. Some of us, not all of us, ham radio operators, we look at that, particularly if we operate HF a lot, although it certainly can be the case outside there. So forecasting the sunspot number is the chief element of concern. I've gone back through almost all of the ARL handbooks as just one cultural indicator of what we collectively say to ourselves. 1940 on, that the sunspot number has been a key element of concern. Some other writers who have prominent important books, like the British writer Steve Nichols, the US writer Eric Nichols. Sometimes these guys get confused when it's just, the book by Nichols. So let me make a distinction there. Carl Lusselschwab certainly is one of the key thinkers in amateur radio, and he writes a good bit about that. He's kind of the ARRL's go-to guy. Tomas Hood, who writes in CQ magazine, I don't think he's written a book. If he has, I've just missed it. So all of these things are focused on two elements of sunspots. One is the amplitude, the peak, and then the trough, as well as the transition from one to another. Those of you in the US may know, I'm old enough to know because I was given these books as a child. The popular Dick and Jane series of books, Basil Reader, it really wasn't about the story. It was about learning words. C-spot, their dog, C-spot run. Well, we tend to see sunspot and C-spot curve, and we do that almost blindly. It's effectively a cottage industry in amateur radio, in books, articles, and online forums like QRZ and EHAM. Now, practitioners in amateur radio and astrophysics both follow this canonical dictum of a sine wave cycle of about 11 years from peak to peak in the cycle, ever since the original observation by Heinrich Schwabe back about 1850. Now, we in amateur radio vary a great deal in our sophistication. Probably the leader in terms of sophistication as a ham operator is Carl Lussenschwab. He's done time series modeling and curve fitting techniques. And yet we have, hams that just take a copy of the last cycle and sort of Photoshop it as a layer on top of next cycle and call it a rough estimate. I'll give an example of that in the next slide. It's really important for us to see that none of these writers offer an explicit theory underlining their forecast models. This renders them to predictive models rather than explanatory models. Now, my mentor in time series modeling was Bob Goodrich. Bob has a company, has a piece of software out called Forecast Pro, uses an early version of AI. It was not that sophisticated, but it was very, very good. Bob is a leading consultant to the Electric Power Research Institute, forecasting electric grid demands here in the US. So that was my background. And one of the things Bob always talked about was, do you just have a predictive model? If so, great. Do you have an explanatory model? Do you understand what you're trying to predict? And I want to make that distinction for us here in amateur radio. Here's an example, Nathan W1YW on QRZ. We get into, okay, what's the next cycle going to be? And believe me, as we all know, all it takes is 1 week of down sunspots. And what's the magic phrase that gets posted? Monderminium. So Nathan published this prediction on QRZ, and he said he did this. He literally took a copy of the previous cycle sunspots and then laid it over cycle 25. You are here, and here they are as a rough estimate. Now, Nathan's a smart guy. He has a PhD. I don't know if it's in physics or math. I know he's taught math. He's claimed a number of patents on fractal antennas. I think there was something on QRZ that he has another patent on some type of antenna, I think. So I want to make this point, and I'm using this on purpose. Nathan's well thought of, very bright guy. I think was at Haystack Observatory at one point in his career. It's not about how smart you are. That if you're just smart, you can predict this better than others. That's not it at all. It's whether you follow blindly, I would say, a paradigm that worships at the Holy Grail of it's a sine wave phenomena, and that's all we need to know. So I'll quickly go through this, but again, I'll use the ARRL as sort of the guide stone here, the 2019 handbook. Since the earliest days, our traditional measure has been a count of sunspots. In hundreds of years, we've learned that it's about 11-year sunspot cycle. It affects conditions because there's a direct correlation. And whenever, as a statistician, when I hear direct correlation, my ears always perk up. There's always a causal argument there. There's a direct correlation between sunspot activity and ionization. Notice there's no discussion of what causes sunspots. They are taken as given. Economists would call that a fully exogenous variable. Eric Nichols has an interesting statement here. Propagation's an art form. We're getting better at it over the last century. It's not a hard science. We can't predict when or how many sunspots may pop up at any time. We're still not sure where we are in the current sunspot cycle. Top experts still can't agree on whether we're going to have the best or worst solar cycle in the history of ham radio or the history of man. On the other side of the pond, as Brits tend to be less hyperbolic, Steve Nichols talks about them in a little more sanguine tone. They're about 10.9 years in average, but they can go from a 7-year cycle to a 17-year cycle. Wow, that's quite a bit of variation. A variation of 10 years, almost as long as a cycle typically is. The maximum sunspot activity varies from 49 to 200 with an average of just over 100. The minimum number can be anywhere from 0 to 12. Steve is saying things in the British form that Eric said in more of an American hyperbolic form. Carl Lusel-Schwab has some very interesting comments, and this is from an undated paper on his website, but he was kind enough to share his now published book with CQ Publications. They did not have it in stock as I was preparing the Radcom papers with Scott. So I want to encourage you to look at his book, particularly chapter 3. And observations that we appear to be headed for another long-term period of lower solar activity. Although what cycle 24 will do is still debated, I believe scientists will have a single consensus for cycle 25. Notice he didn't say model, he said consensus. It will be low, followed by several more low ones. Of course, the history of the sun may not be a good predictor of future activity. Not only don't we fully understand the solar cycle process, we only have a couple hundred years of data for a process that has likely been going on for thousands or millions of years, and that's a small sample size indeed. So what Carl is implying here is that if we just had not a couple of hundred years of data, but a couple of thousand years of data, we could just model this curve better and better, and we could just figure it out, that the curve is in its own self what we need to understand. Now, all leading amateur propagation experts make use of this sunspots cycle paradigm. Follows 11-year sine wave period, originally follow it. Now, that's been accepted canon for over a century or more. But as Eric Nichols exclaimed, we still can't figure these things out. So from a philosopher of science perspective, the devotion to something that's theoretically unexplained but taken as given in the face of empirical anomalies at face value is puzzling. I think Mr. Spock would say that is not logical. So in the absence of theory to articulate the causal antecedents of sunspots, this insistence that sunspots are what their counts are, really leans toward what we would call in philosophy of science, scientific teleology. That is, some phenomenon is what the measurements are. You have no doubt heard this. What's human intelligence? Oh, it's what the IQ test measure. Well, everybody back to Immanuel Kant, Nagel, and more recently Barrow and Tipler's summary talk about that is teleology. I think to put it in amateur radio language, it has the problem of bass awkwardness. So this teleological bent, however, is practical. Why is that? Well, we don't question what it is because we are just following along the solar physicists. I'm not throwing stones at Carl or any of them. I'm just describing what our currently accepted paradigm, often taken for granted, is. We're just following along. It begins in solar physics. Why is this? Let's go to some first principles. And here's a little video. Nathaniel, if you can't hear the audio, please let me know and we'll try to fix it.
At Kitt Peak Observatory in Arizona, solar astronomer Matt Penn studies this solar surface to discover how photons of light get trapped.
There's a bunch of theorists today, but hopefully we'll get some data.
Using the McNath-Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun. But they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space. And so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth.
Okay, now I've got one more little animation that I would like for you to look at this part of the graphic and just to illustrate how strong sort of some of the magnetic reach is. You're going to see in it a little explosion here. There you go. And look at it being sucked back in so very quickly. Sort of amazing. So like electricity, magnetism has opposing poles, and we tend to deal with electricity a lot, you know, on amateur radio. We may deal with magnetism, you know, not as frequently. So the sun's behavior, particularly internally, is thought to be a dynamo involving magnetic forces. Paul Charbonneau's constantly updated paper in Living Reviews in Solar Physics. He's one of our Canadian friends who's got just a great explanation of different dynamo models about how the sun works. Hopefully the Parker probe is going to tell us a lot more in terms of empirical data. So the issue about magnets is it will be vital to our better understanding what shapes or causes sunspots and some of their behavior. If you recall the movie The Graduate, I'm dating myself, I realize that. Dustin Hoffman's character, as he was graduating college at a cocktail party, had someone whisper some career advice into his ear. Some of you may remember what he was encouraged to get into. I guess this was from the 60s, and that was plastics. Well, if this were The Graduate, it would be magnets, get into magnets. Let me give you a little example here. Here are a couple, look like dimes. They are some little small magnetic discs of rare earth magnets. I use them a lot on my workbench to mount equipment. Now, here I've really got to work at trying to put these poles together. And what do? They flip. And I wanted to just kind of make that point to us all. We all did that in grade school, but sometimes we forget. Now, what would be the order of magnitude of difference in magnetic force between a couple of little rare earth magnets bought off of Amazon and the sun? Million, billion, gee, how many orders of magnitude stronger? So how did we, magnets, key thing here. I want to refocus our mind on these kind of dynamics. But then how did sunspot behavior get to be a cycle? Many of us may know this. Many of us may have read Schwabe's original stuff. But there's a key from my perspective that it's important to know that it became a cycle not based on a theory, but based on a common scientific inductive inference. So Galileo said to have recorded some sunspots, but Heinrich Schwabe, born 1789, died in 1875, is credited with the first compilation of daily sunspots, the first sort of empirical data set. He's an interesting guy. Here's a little picture of him. He ran a pharmacy. Why? Well, it was a family business, but he had time to do stuff like this as a pharmacist. If anything, he's dedicated. Many of us keep logbooks. Remember, we used to have to keep logbooks, and we used to have record certain things about our transmissions in our logbooks. Well, think about this dedication. In his logbook, one of the things I read in preparation for this, he had his entry of that day of sunspot activities. Well, he noted that his wall clock had stopped with the hands going up and down. And, oh, by the way, his wife died at 9 p.m. that day. It sounds kind of funny, but it's sort of indicative of who the person was. So he began to collect beginning in 1826 on every clear day. He'd scan the sun and record sunspots. It took him 17 years. And he sort of went, there's a pattern here. And it's a regular variation over a 10-year cycle. I said 10, not 11. I'll come back to that. He published this in a paper in 1843. Well, it was a big yawner at the time, but very few people paid any attention to it. But others did later. That's not uncommon in science. So the periodicity of sunspots is now fully recognized, and Schwabe has the credit for one of the most important discoveries in astronomy. On the right here is a scan of just one of his recordings where he made a circle for a disk. He divided into quarters and he recorded numbers. You can see a summary of some of these numbers. And this was in Dessau, Germany. And here's a little statement: is there can be no doubt, and so on and so on. There's some problems. There's a tilt from where he's at on the Earth relative to the sun. So he sees a disk that someone else may not see exactly. Okay. And these little dots prove to be a little bit of a problem. You know, today we try to create metadata and code books, as we used to call them back in the 60s and 70s, of just what all these numbers mean and how they were developed. But nevertheless, that was an example of how the beginning of sort of sunspot science originated. Here's a little chart by David Hathaway, who was at Huntsville at the NASA Center there. And you can see the beginnings of a crude sine wave over this period of time. What's really important for us to realize is that he made an inductive inference about one of the sun's systematic behaviors without any formal theory. In other words, he didn't predict the presence of the rise and fall ahead of time and then observe the data to verify his theory. And this is really important. We'll come back to this. The Swiss astronomer Rudolf Wolf was so impressed, he spent 40 years. Imagine you being so impressed with someone's fledgling work that nobody paid attention to, that you would spend 40 years digging through archives and compiling a history of sunspots as far back as 1745. He figured out, wait a minute, Schwabe did good work, but I'm getting 11 years. To a statistician, this is not shocking. Anytime in a long series of data, you take a smaller slice, you can easily get some characteristics that do not generalize out to the full. So that's where we get our 11 years, although Schwabe's, his little slice of data in the long run history was 10. Let's just take stock for just a second. Let's look at this diagram for just a moment here on the left. Standard thing that we might see back from cycle 1. We have these peaks and valleys. Down here, you can see the troughs a little better. You've got some troughs that are narrow. You get some that are wide. Gee, look how wide that one is compared to these previous ones. It gets some narrow ones. So if you're trying to say, hey, when's the next one going to kick up? You can see you've got these variations in the trough here. So here's some observations that I think we can all make. I certainly make them. You may make some others. I'd love to hear what they are. We have a regular movement up to a peak period and then back down. That's pretty clear. The peaks are not consistent, with some higher than others. Well, I think you'd be hard pressed to find any subsequent peak that's exactly like, more or less, the one previous to it. You get some like this one's almost what that one is, but then there's another peak between it. So they're not consistent with one another from cycle to cycle. So the cycles do not wholly replicate the previous one, either in their peak or in the length of their trough. There's irregular gaps between one sine wave cycle and another. So it begs the question, does it make sense to assume that sunspot cycles are only caused by previous cycle behavior, no matter how many years of cycle data we might have or don't have? Does that make sense? My argument and Scott's argument is no. Let's transition for a second here to official predictions. I'm going to say some things that may be surprising to some of you. It may not be to others. We only have a translucent view by the public into how the scientific sausage is made in the official sunspot predictions. And the last 3 solar minima of cycles, 3 times 11, about 33 years, so several decades, NASA and NOAA have combined to convene panels of experts. They're experts in solar physics, time series analysis, and other associated areas to assess and forecast conditions of upcoming maximum activity. We all have a great love for why these are important. I won't even go into that. So this is an important forecast. Maybe surprising to hear that the official NASA NOAA solar cycle prediction panel does not give a detailed documentation of their methods so that other scientists or practitioners can replicate them. Now, that's just a standard canon of science. You would never be able to publish an article in a peer-reviewed journal if you didn't disclose what your methods are. Now, the amateur operator Eric Nichols says in his book, and I think we can all agree if we're scientists, good science is subject to peer review. So the scientific data panel releases data points that represents their forecast, but they don't give us the detailed methods used in creating those numbers, whether it's by model or what. If you look at the panel's documentations, and I've requested others, I didn't get a response. That's their standard practice, as I understand it from Scott. They disclosed that, okay, they had a wide array of submitted approaches to them. They had 61 different predictions by others submitted to them in the RADCOM paper that Daniel has uploaded to chat. I've got all the citations to anything here. And there's a smorgasbord of different approaches: climatology, dynamo theory, machine learning. Everybody's doing machine learning. Going back to prior stuff, neural networks, back in the 80s, precursor models, spectral and statistical models, solar flux transport, and other. And what they show in their PowerPoint, which is the only thing they release, you got an average cycle 1 to 24 peak of 112. The average of all predictions is about 87. They show you how these different content models, for lack of a better term, where they stack up here. This is version 1 of Sunspot numbers, and it's version 2. Those of you who followed Wolf will know that there are 2 different versions of how sunspots are counted. So that's what the panel says it does. Now, to be fair to them, their challenge is not to create a model, but to use state-of-the-art knowledge to develop a consensus estimate rather than a model of the sunspot cycle maximum amplitude and when it will happen. When will cycle 25 begin, and what will be the peak? Well, they've not had a great deal of success in estimating the timing or the strength, honestly, over these 3 past cycles. So these panels construct this forecast through a democratic vote of the panel. Now, I've served on the Advisory Committee on Agricultural Statistics for the Secretary of Agriculture for 6 years. That is a panel that takes a vote and makes a recommendation over the scintillating definition of what an American farm is. That may make you laugh, but it hinges, that decision determines where billions and billions, to quote Carl Sagan, of dollars go, because each state's percentage of the total number of farms in the U.S. shapes food stamps and a whole lot of others. So I've personally served on groups that operate to a democratic vote. So I'm voting as a scientist along with somebody from the agrochemical company. Now, there was a great article that's cited in the RADCOM paper. If you can't get Science Magazine, email me offline. I'm good on QRZ. You can find me pretty easy. I'll send you a copy of it. But Sarah Scholes, a science writer, covered the last panel. You might find it of interest. The last panel met in the floor beneath Scott McIntosh's office out at NCAR. Kind of interesting. He wasn't invited, but it met on the floor below. Now, Scholes tells us a bit about the panel's discussions, and Rachel Howe of the University of Birmingham, Birmingham, as I think it will be pronounced, in the UK, she reviews statistical models and said, well, there's not much physics and there's not much statistical sophistication either. Now, of those 60 or so odd models, Chairman Bisecker, he kind of says, we haven't really found one that seems to work, and we've been doing this for hundreds of years. And the final vote came with this admonition by the chair: consensus among experts can often be a better prediction of the future state of a system than the set of individual predictions. Excuse me. He's got a point. I've been on some of these things, but I don't think hams writ large know that. I don't think we really have had a reason to understand how those are made. We don't know how that sausage is made, except it's a democratic vote. There are legitimate methods to average forecast models, but we just don't know what they did. I'm sure all of you hams here in the audience particularly are familiar with the spaghetti models of hurricanes. And very often the European model, of which there are a bunch of lines, and US models, of which there are a bunch of lines, they each have different assumptions. Sometimes those are averaged. Those averages don't tend to work out very well either. So there are situations where experts have a collective professional judgment, such as the National Bureau of Economic Research, which is the body that gives an official recommendation on whether we're in an economic recession or not. That's not based on a model. That's based upon a professional judgment. But let me compare this to the report to the president on the economy by the President's Council on Economic Indicators. If you've ever read it, you know that there is a boatload of appendices with data, model results, and assumptions. The same kind of report is presented to Parliament in the United Kingdom. So even what we collectively might call the dismal science of economics documents what they do. One thing I think happens with amateur radio is the image that we have for NASA and NOAA. Here's a couple of news articles. NOAA triples its supercomputing capacity for improved storm modeling. A pair of 12 petaflop General Dynamics systems cost a cool $500 million. The joke on the Hill in Washington was, yeah, they want some more of those GD supercomputers when they were funded. On the right is the Pleiades supercomputer built by Silicon Graphics out at NASA Ames in Mountain View, California. Now, I worked for NASA under contract in the late 1990s, was a badged official at Stennis Space Center and their commercial remote sensing program, where I coordinated a $60 million program. I'm a certified storm spotter, as many of you might be. I've taught meteorology students when I was at Mississippi State. They took my GIS and remote sensing classes. I've seen a lot of NOAA-based data, and they both have tremendous supercomputing capabilities. Now, I think many of us succumb to the image of NASA NOAA. Heck, NASA put somebody on the moon. They're going to put somebody back on the moon, I hope, beginning on Saturday with the successful launch of Artemis. We have that image. However, this panel that is sponsored by NASA NOAA don't appear to create a forecast model. They only have a reputational vote. I'm not beating on NASA NOAA, but I don't think we know this collectively. So I just want to keep that in our mind. We don't know how the official models are created. Well, this leads to a challenge when you have someone else like the Macintosh team. How does science work in terms of identifying scientific paradigms? How they operate over time and what leads to them changing? Now, Nathaniel has been very successful in pounding the drum in his area of science with the National Science Foundation in convincing them that amateur radio has a citizenry, scientific citizenry might be one way of putting it, where we've got sneakers on the ground, where we can collect really good scientific data and do a lot of things far more cheaply than many other programs will have. And he's kind of competing with some other paradigms about institutional science to do this. So that's kind of what I'm getting at. The tendency for an area of science to remain confident in a singular approach that doesn't work that well. Now, remember, I quoted fellow hams. We don't know a lot about this. Carl would say we need a lot more data. We don't have much data. There's an assumption there. But one of the best ways of understanding paradigms is through the physicist Thomas Kuhn. He defined the paradigm as the broadest unit of understanding in a specified field of science. And this is in his famous book, The Structure of Scientific Revolutions. I've used that with agencies to help them understand, what they're getting in proposals and that sort of thing. So here's a figure of Kuhn's model of science's progression over time, has different stages in it. And I've tried to annotate what Kuhn says about each stage and then plugging in the corresponding stage for the Macintosh paradigm versus the existing paradigm. I'll give you 1 second just to look at this. There's a lot on here. I apologize. Before we have a paradigm, Kuhn calls that pre-science. We might have some data, we might have some observations, but we really don't have a theory, anything we can articulate. If you're in a given area of science, other science say, well, what are you? Now, what they're referring to is what is your specialty? And if you say, I'm in specialty X in biology, they might say, oh, so you use these high-powered microscopes. Yes, I'm a molecular biologist. This is kind of what I'm getting at here. The lack of a broad unit of consensus about an area of science is pre-science. We might look at Schwabe's log of observations and his inference of a 10-year cycle as being in that period of pre-science. Even Wolf's subsequent big database, that may have led to a sense of the sine wave paradigm. That's what solar sunspots are. It works on its own energy, if for lack of a better term. So we get into normal science, and that is what Kuhn calls puzzle solving. The scientific community knows what the world is like. Students in the paradigm are trained to believe in what this theory is. I suspect, Nathaniel, you've taught many of the fine students that I've seen you have there at Scranton. Hey, this is what you need to learn. Here's what we need to look at. And here's largely what we're going to see. And here's kind of what it means. This is puzzle solving. And when I've given talks to lay audiences, one of the questions that I've always gotten about science is, why do you scientists just write journal articles to each other? Yes, we are writing articles to each other, and we should be. We shouldn't always write scientific research articles to the layperson. We have to talk to one another. Now, I'm not saying that shouldn't happen, but science writers do a pretty good job writ large at doing that sort of thing. This business of puzzle solving is what Kuhn describes as what drives scientists on. That next little chink in the paradigm, I'm going to solve this. Every dissertation should solve some puzzle in a paradigm to make a contribution to knowledge. And if it don't fit the paradigm, it ain't a contribution, right? Predicting sunspot cycle based solely on past cycle behavior characterization over an 11-year period, that's kind of one of the things, and we can do searches and see just oodles of articles that use one model, another model. I brought this in, I brought that in. We are going to town with normal science here. However, there are anomalies. We missed the mark. And when that happens, the scientific community writ large said, yeah, well, you did something wrong. Well, go back and get more data. Well, no, that's not supposed to happen. It's okay. And I think Eric Nichols' comment, top experts still can't agree whether we're going to have the best or worst solar cycle in the history of ham radio, sort of typifies when you begin to get anomalies, people start, yeah, okay. Then it really turns up a notch. If enough of these anomalies occur, so that there's less of an ardent behavior in believing in a given paradigm, and people begin to get worried. In 2012, Scott McIntosh and his team submitted a paper that I had the honor of reviewing a few years ago, and I marked it up outside my field of science, but I certainly marked it up and got it back to Scott, and that kicked off our 2-year-long discussion on some of these things. When that happened, model drift, you've got another way of looking at things. You know, you get somebody who's peer. I've started 2 journals and I've been associate editor of others. And what happens with reviewers say, hey, Frank, did you get that paper that Nathaniel submitted? Man, I said, no, reject that. We can't let that kind of stuff. We can't let those amateur radio operators in here. I may not get my grant proposal funded. We've got to maintain what we're doing here. Whether you believe it or not, those things do happen. And so when the Macintosh team submitted that to science, whoever the reviewers are, without question, begin discussing, who is this heretic? He needs to get on board here, or various versions of that. Now, the next stage from model drift is when there's enough attention by scientists to say, you know, we haven't gotten very far in a while with this. And there's this other group over here, this other person who's kind of doing something different. And I saw another article by them. Maybe I should look into it. So when McIntosh's team continues to publish data, that tends to gain peer reviewer support. Now, I know one paper, the first key paper that they had a hard time getting published, the reviewers kept upping the ante of how much more data. So finally, Scott went back and got all the data that's out there, period, forever, that we can get on sunspots and what he was trying to measure. And in fact, I encouraged him to look at some of the leaders in the area who might be negative and point out what standards they use, how long of a run of data did they use and what they were doing, and point this out to the editor. Having been an editor, I know that every reviewer is a would-be author. They really want to author the paper and tell you how to rewrite it, and I do it this way, don't do it that way. So when McIntosh et al. Continued to publish, that set some things in motion. Potential for a model crisis. Which one are we going to follow? Well, it just depends. There are a lot of competitive models. Those of you who might remember cold fusion that was developed out in Utah, where the state put a bunch of money in on some stuff that proved not to be so. There's a great book called Bad Science that documents that failed competing paradigm. So guess what happened? There's the official predictions that are put out, and then Macintosh teams, they put their predictions out. I showed you that in the first model. When that got to be made public, suddenly you've got model competition. A competing paradigm offers a model that is more consistent with instrumental observations at the core of the science. Moreover, it explains the key phenomena more accurately. Right on to the bone last month, were we? And with greater theoretical understanding. There's an actual peer-reviewed theory construction that Macintosh team has published, and yet maybe not crickets, but no real disclosure by the NOAA NASA team. Now, I think we are here. Having advised some agencies about where certain areas of science are when they get ready to go to Congress to ask for different amounts of money. I've been on the congressional side where my congressional delegation asked me, look, what are your thoughts about this? Anyway, we're here. And if that model gets so much traction that it's just better than the old paradigm, there is not a collective set of beard scratching here. A little bit of a sexist term. I apologize for that, but that's the term that's kind of used. No, it's like rats from a sinking ship. Those that see a new paradigm, a new buzzword, whether it's AI, which is right now, put AI in your proposal, they're going to fund it. That's like rats from a sinking ship moving through that. A model revolution and a paradigm change. It's not slow. It can be very quick. You think mRNA and genetics is going to get funded after COVID? You bet. So what is this new paradigm proposed by Macintosh team? What theory do they have to explain some characterizations of the sunspot cycle? Now, a picture here on your left is the closest picture of the sun to date from a probe mission. No, it's not that orange shag carpet from a fraternity house in the 70s that had a lot of parties dancing on this floor. It's plasma directed by magnetic flux. Wow, look at all that activity. Here's a model of some of the magnetic lines from the core of the sun and emerging in different spots from the sun. We're going to use these as metaphors here. Now, here's the kind of the statement in the unpublished manuscript that was rejected by Science. They've never published that manuscript, but they've taken parts of it and published it in pieces. We present a new observational paradigm to illustrate the production of the approximately 11-year sunspot cycle. Here's the new idea. The observed features are part of the 22-year magnetic activity cycle. Sunspot, subset of the magnetic cycle. That's why I showed that movie to begin with, where the modulation of the sunspot cycle, its rise and fall, is a direct result of the interaction between, here's a new phrase, temporally overlapping activity bands. Temporally overlapping activity bands. I'm going to show you those in just the next slide or two. And the key is the realization that magnetic flux associated with deep-rooted magnetic flux tubes. You know, it's not like cutting the frog open and looking at the ventricles of the heart. We don't get to go inside the sun at this point to see these. So this is a theoretical mashup here. But this is in a coherent fashion several years before the sunspots appear on this equator word trajectory. That'll make more sense here in a diagram. Now, the reviewers sort of rejected this because they were following the Kuhn model, boundary maintenance. It was a tough start. 10 years ago, this team didn't stop. They persisted. I want to point something out, and I know Ward Silver's here. I don't know if he has an understanding of this or not. Not saying that you were around at ARL in 1940, Ward, but in the 1940 handbook on page 319, it was interesting. The statement, the ionization, blah, 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 variations following the 27-day and 11 or 22-year sunspot activity cycle. That didn't have a source reference, and it was repeated again in 1941. And apropos of nothing other than that's the only other time I've seen anything in amateur radio that mentions this 22-year thing as opposed to the 11-year thing. Hey, maybe the ARL was on to something way ahead of their time. So let's look at this prescient idea of the Macintosh team that the Hale cycle is part of it. Here's our standard sunspot number cycle, sine wave, and so on and so on. Here's the little one that Nathan W1YW. It's what I call the Cookie Monster part of the thing, or it's Orca getting ready to eat something. Here's the Hale cycle. These are magnetic bands, and here's the latitude of the sun. 0 would be the equator, of course. Here's one polarity. Remember me showing you the little magnets here. Those are polarity that repel. This one attracts. So notice what happens. You have two of these. You have two of the sunspot cycles over one magnetic cycle. And guess what? You see the flip from one in one equator versus another. And then over time, there's this trajectory of these magnetic bands toward the equator from up about 55 degrees latitude down to their steady march to the equator. All right. So this magnetic band polarity flip that George Hale identified years and years ago coincides with this approximate sunspot cycle thing. That's interesting. What about these temporal movements across latitudes? But as McIntosh and his team have found out, which much better data than George Hale ever had the opportunity to get, yes, they are connected, but in complex ways and means. I won't go through every one of these, but I want to hit you with some terms here that are important. So the approximate 11-year sunspot cycle is just kind of one half of the Hale magneto cycle. It's a direct result of the interaction between these overlapping bands. You see how the red, blue overlapping bands, that's what I'm referring to here. That interaction is key. Now, those of you who've been around computers for a while may have heard of the Bernoulli box, and the mathematician Bernoulli had a mathematical theorem that showed that if you get things in magnetic polarity in the right way, it will be extremely steady. So those Bernoulli box disk, I had two 10 megabyte, I know you're jealous, two 10 megabyte disk in a Bernoulli box back in the 80s. They can get very, very stable. So imagine if you had a run of these things, what those forces might do. It might direct those filaments in certain ways. And that is what McIntosh is saying, this with deep-rooted magnetic flux tubes from one part of the sun through its interior to the other. the term polar convective recycling time, moving from 55 degrees down to the equator. And then what happens? They cancel out sunspots. And then, as John Madden would have said, diagramming an American football play, then boom, they go back up to their point in the equator. The key thing is what Scott and his team called terminator events. We think of solar minimum as the end of a cycle. It makes sense. We look at it, it's at the bottom, and then it goes back up. Well, and then the maximum would be the maximum. Those are cardinal markers. However, their team argues that that is like a watch that doesn't keep good time, because that's an outcome of the underlying causal factors that in from the Hale cycle that influence the sunspots. It's the terminator to terminator period that are really the more accurate and causal markers of the change of one solar cycle to another. Now, it's imprecise from the trough or the peak, because a tsunami of magnetic activity, when the new solar cycle is kicked off, it's when, as I said, the John Madden boom happens, when it rushes from the equator back up to the poles. The thing that's more important to us, I think, is that the length of time between one terminator and the next one is what shapes how high the amplitude is going to be in the next sunspot cycle. Here's a picture. You're going to see some animations of this very, very quickly. And I realize it's taking a little bit of time, but it just takes time because it's nuanced. Here's George Ellery Hale on Wilson Observatory near Los Angeles. Notice how his little machine for recording these things is not terribly different than what you saw at Kitt Peak out in Arizona. And here's a little backstory. As Los Angeles urbanized and pollution got bad, that observatory's operations basically moved to Kitt Peak. So what you saw in that video is the heritage of George Hale. You read this delightful little article on the probable existence of a magnetic field in sunspots. He connected the northern and southern hemisphere magnetic bands having opposite polarization. They flipped around the minimum observed sunspot numbers, only reversing again at the next solar minimum. And his work is legend in solar physics. And he argued basically that as this equatorward movement happened and this polar flip from one equator to another one occurred, it's connected to the rise and fall of our sunspots. Here's one where you've got these tubes and the movement at this point in time. These are connected with the upper panel, sending phase of sunspots. Then it peaks and then begins to decline. And then it's at its minimum. And as you see, boom, it goes back up to about 55, 30 to 55. Here's a little diagram of the torsional rotation. Remember that 70s shag carpet? It didn't get that way without stuff happening. And here's a model of some of that happening. All right, now, so the terminator event, I want to show this to you. These dashed lines are a terminator event demarcation. Here's the solar flux index over these years, and I apologize for that being grainy. And it has a statistical and mathematical correspondence with the sunspot number. These are sunspot numbers for different hemispheres. Here's the overall sunspot number. Now, for many years, solar physicists may not have had the data capability before computers kind of surged and to handle a lot of these kind of data, but we do now, and Scott certainly made the best of it. The Hale bands are identified through EUV bright point distributions, these bright spots that are measured regularly by these organizations. And you'll see as they race toward the equator, and we've got the minima of the solar cycle, and then boom, back up, and then they take off. This is part of the underlying, and you see in the lowest one, This is the underlying causal features, McIntosh's team thinks. And this is why looking at it as the minimum or the maximum, you're looking at the wrong thing. You're out of gas before your gas meter in your car knows it. Now, here's what's happening when there's a boom and it goes from the equator, which is right here at 0, back up. There's this tsunami. Dick Potty and others, of which McIntosh is one of the co-authors here, is there's this flurry of magnetic activity from the equator back up, and these white lines are when the sunspots begin to just take off. It's like spring and amateur radio. We got a new solar cycle, man, the bands are opening. That's what this is a model of. This can happen in one 27-day solar rotation, in a heartbeat in solar physics time. Now, to tie this together, here we've got a disk of the sun, we've got the magnetic bands, we've got the Hale cycle over here, and then we've got the sunspot cycle. I'm going to turn on this animation, and you're going to see it go to the equator, and when it does, it chokes off the sunspots, or at the minimum, what we typically call that, and then boom, when this thing flips, look at where the polarity flips and look at how sunspot increases. And you'll see it going from the equator, and then it will get brighter up here. We play it one more time. So you can see when it flips and it jumps, that's when the new cycle kicks up and gets into gear. But we still haven't explained one key thing. Notice this one got this high, this one got that high, that high, that high, that. What determines how high this is going to get? We've established, at least from this paradigm, how that happens. So we still got one thing we've got, at least one thing we've got to figure out. And that is this: the difference between one terminator and the next one, it shapes the following after the two terminators, that distance, that length of time in years, for example, it shapes how high the next solar cycle is going to be. So this is the delta, the difference between the preceding time periods, the delta there for, say, 24 and 25. Let's look at 24. This was cycle 24, and this is the NOAA NASA prediction. Remember, they said, it's just going to kind of be like it was. My friend Carl Lusser-Schwab says, yeah, it's going to not be so great and going to be continued even further like that. And W1YW taking just, he was well within this paradigm to just photocopy the previous one and put it over here. But as that guy on ESPN, that older guy, says, not so fast when you're predicting Clemson to beat Georgia Tech this Labor Day. I'm a Tech fan, sorry. Using this different paradigm, look at what's predicted. If it's the delta in the previous time, what's the difference between cycle 24 and cycle 25, not taken into account by NASA NOAA? Look at what the delta was for cycle 24. It was 13 years. What was the delta for 25? It was a little over 9 years. So that, in the overlapping magnetic cycles with the sunspot number, in that 2020 paper, that was a truly kind of breakthrough argument and paradigm with supporting data by the Macintosh team. Now, more work has been done, and I'll wind this down. Bob Lehman in Maryland, who's one of the Macintosh theorists, has created a solar clock. So you'll see that these green dots are here at the minimum, these red dots at the maximum, and here at the terminator, these blue dots, and there are these disturbance storms. We've got different types of flares. They're doing great work and putting together a solar clock, because as Carl Lucerswab wrote me, okay, you're convincing me. He's changed his mind on it not being so great. He thinks it is going to be great. But when can we predict the Terminator? Well, we're beginning to put that clock together, or at least we being the Macintosh team. Now, here are the two predictions for NASA NOAA. Here's NASA NOAA, and here's the Macintosh team. Quite a distinction. Now, this is even given the NASA NOAA team their 6-month shift that they wanted. One thing about Macintosh's predictions, it tapers off a little quicker than this. I guess the higher you go, the quicker you fall, but we'll see. So those are the two predictions between the two. Here's the solar flux index prediction. It's in the Radcom paper part 2. I'm going to ask Scott for the data in a spreadsheet, and I'm going to put the major contests out there for this coming cycle and kind of post them somewhere. And we can just see, if cycle 25's SFI at that period was better than the previous contest, what can we tease out of contest data about contacts and stuff like that? Might be fun. So this recent paper, Timing Terminators, they have a new method of forecasting the timing in one of their papers, and it was a little bit of a controversy. They had to make their arguments. I've taught engineers statistics for a long time. I've been around engineers a long time, and training undergraduate engineers into a culture of think like an engineer is great. I used to be asked to go give the banquet speech at the College of Engineering at Mississippi State by the dean to talk about science and career development, which was one of my core areas of research. And so it's often, as the old statement says, give a small boy a hammer, everything looks like a nail. Learn fast Fourier transforms, everything needs to be FFT'd. I use FFTs every day. We all do in amateur radio, and that's great. But there's a room for a Phillips head screwdriver in addition to a flat blade, right tool for the job. So the Hilbert transformation allowed them to develop a robust signature of terminators in the Sunspot records, and they used an extrapolation of the Hilbert phase of the sunspot number and the solar flux index, so they can predict terminators much better than using the methods that they used initially by using a lot of raster data, bright points, and versus an equation. As my friend Joe Barry, who was one of the leaders in early GIS, used to say, raster's faster, but vector is corrector. So what's the comparison of the two predictions here? Here is a dressed up version of that graph I showed you earlier. Here's the current sunspots. And I just want to point out, at what point, big if these lines hold up as predicted, will the NASA NOAA paradigm kind of be in crisis, the reputational vote, as opposed to a theory constructed based upon clear ideas from solar physics and empirical data that, gosh, at least from end of July, just right on the money? Will that be in a crisis mode, to quote Kuhn? Or are we on the cusp of a scientific revolution in sunspot models? Well, I think that scientific philosophy, the new peer-reviewed theory construction by the Macintosh team, and their empirical models say we may well be. Well, a century ago, the literate world waited while some photographic plates were taken of the 1919 solar eclipse. Albert Einstein's sub-theorem of equivalence, he said that light would bend, and we could test this if we got some solar plates from certain places on the Earth to get the right angle. So be it. You're going to challenge Newton, huh? You young whippersnapper, Einstein. Okay, well, the Royal Society and the Royal Astronomical Society, they funded expeditions by Eddington, Dyson, and Davidson, and they went to Brazil and the Island of Principe to collect these solar plates during that eclipse, and the literate world waited for results. I've put the headline of the November 7th, 1919 Times of London newspaper. It was Revolution in Science, New Theory of the Universe Newtonian ideas overthrown. Now, history shows that Einstein's challenging paradigm shift was indeed supported, by those experiments. And the London Times kind of said it. And my statement in Radcom about this was, who now reads Newton for science rather than history? So we invoked this thing to bring about how scientific and paradigm clashes and crises can play out. They can result in a crisis state. I think as the sunspot cycle continues, I think we're in one. The central question is, at what point, with this divergence continue, will you think we're in a crisis? I can think it all I want, but until there is a collective group of practitioners who believe that this new paradigm has got more going for it, then it'll just be a competing model. So will we be on the cusp of a scientific revolution? We may well be. What's different now than it was a century ago in 1919 is here is a website that is updated monthly, and you can follow along with the sunspot predictions to see who is right. So that's it. I'm certainly ready for any questions, comments. Fortunately, we're on Zoom, so you can't throw rotten tomatoes at least and hit me with them. So I'll turn it back to you, Nathaniel.
Thank you so much, Frank. I really appreciate that. Let's see, we'll take a few questions.
I have a question.
Yeah. Go ahead, Tim.
Yeah, this is Tim Barrett, K9VB, and I'm a member of RSGB, so I've already read those two articles, and I thought they were absolutely fascinating.
Thank you.
One of the things that I recall Thomas Kuhn saying is that the transition from one paradigm to another, it can take a long time, because basically you have to wait for the scientists from the old one to die or to retire. But I would think that what we're seeing here is something that should be pretty rapid. As you said, everyone can look at these numbers. And if we get to 24, 25, and we're seeing that it's still following Macintosh and not all of those 60 others, isn't the old paradigm just going to be dead in the water straight away?
Tim, you have raised a very good statement. Now, you are correct. And again, Thomas Kuhn, a physicist himself, writing in the 60s, and there's been a whole lot of work on Kuhn written since then. But if you think about where paradigms are held, they're held in universities and research centers because they produce subsequent generations of students. And remember the old dictum, what's a good dissertation? Someone would say it's a signed dissertation, signed by your committee. So to some degree, you have PhD candidates who, if you will, follow along, just like we hams have followed along in solar physics here without questioning. We had to. We don't really have the collective wherewithal to do solar physics better than solar physicists. So your point is, I think it hits right at the heart of the matter. Sometimes the so-called old guard wants to invoke boundary maintenance. Well, today things move faster in many ways, partly due to what we're doing now, the internet. So Tim, I would ask you this. I've already stated, I think we're in crisis, clearly. I think that gap is there enough to where there's a crisis. But Tim, let me throw it back to you and just ask you a question, because it really will depend not on people like me, but on people like you. When would you say, I think the Macintosh model is the way to go? At what point in that diagram would it be enough for you?
I think I'd want to see a whole cycle. But to me, just the sheer fact that we have a difference between a predictive model and an actual method of what's going on makes me lean very much towards the Macintosh. I read about it last year, and as soon as I read it, I thought, this guy must be onto something, because he's actually got data to support him, but he also has a mechanism to support him. So I think it's already, a long way forward in my view.
Well, Tim, you said something that kicked this off. And I want to be fair to NASA NOAA. The old Pogo cartoon, we've met the enemy and R1. Well, I used to have a NASA badge. I've worked it now. I think highly of NASA. I got no criticism of NASA. I think, though, that we amateur radio operators collectively, now there are individuals who do, but collectively, we don't really follow how the official predictions are done, because they aren't disclosed. So here you've got two competitors, okay? You've got one competitor that doesn't tell you how they got their numbers. Okay, well, why not? I mean, if you just said we averaged the model submitted, gosh, in the absence of a competing model, okay. I mean, we do that in meteorology with hurricanes. We average spaghetti models sometimes. We do that with some other things. But you've got what I call at best a translucent paradigm. They don't disclose their approach and that sort of thing. On the other hand, with the Macintosh team, you have a formal theory, formal in the sense that they published it, they tell you what they're doing, they will disclose the data. Here's even a website that's tracking it every month. So you've got kind of a weak position in the NASA NOAA panel. It's just, we were asked to do this and we've done it. This is not our day job. We're on this maybe for a few months. We may get reimbursed for our travel. It's not a full-time job. Well, this is Scott's job. Now, he's also an administrator there. So, I agree with you. I think this transition could be volatile, especially by the end of cycle 25. I think if it holds up like it is today, not everybody believes it will. I gave this talk to a group called Cycle 25 that meets on Saturday morning. I won't name the well-known ham. He's got a well-known YouTube channel. He said, well, it just might not. It just might not. I said, okay, let me bet with you. I'll bet $100 US that the sun will come up tomorrow. if you'll bet against it. Well, he wouldn't. I said, well, okay. The logical possibility of the sun might not come up tomorrow versus you're willing to bet money on it not coming up tomorrow is quite a distinct thing. The old vicar Thomas Bayes would talk about that in terms of probability and Bayesian theorems about probability. So Tim, you're spot on, and it's because we don't have a disclosure. The easiest thing would be, from my semi-outside point of view, would be for the panel the next time they get appointed is to appoint McIntosh and some of his team on the panel and then come out with a model, whether it's his that's been modified. Yeah, I don't know. But we collectively need to understand that, certainly in amateur radio. So that was just a great question.
Thank you.
Question, Larry in 6NC.
Go ahead, Larry.
Okay, Frank, please, can you go back to that, the graph where you showed under the Macintosh model, sort of a pinched haystack peak?
Right. So I'm going to go back and you tell me, let me get this thing started here. And
the one you said it was faster up and down to the peak of the cycle.
Tell me when I'm there.
Yeah, that was it, wasn't it?
This one?
Is that the one you commented it was steep up and down?
Yeah, it's this one. Yeah.
Okay, my question is, does that suggest either way that the magnetic cycle has more of a constraining influence on what happens in the sunspot cycle than what we've been calling the sunspot cycle, the 11-year sunspot cycle?
Well, one of the points, I'm sitting on a orthopedic pillow. came from a neurosurgeon yesterday, and thank goodness I don't have to have surgery, but I do sit there, so I had to adjust myself. Sorry. Clearly, the Hale cycle and those dynamics identified by the Macintosh team, they claim, clearly shape this red line going up and down. We don't know what shapes the purple line because that's the prediction panel, and they don't say what model they used. I mean, they just hear our numbers. But clearly, the rise to the peak amplitude is governed by the difference between the two terminators, what they were calling delta, in this diagram. The difference between the terminators. And just so we're all clear, remember this distance from this dashed line to that dashed line here. In other words, this difference in years will predict the peak of the subsequent solar cycle. That is the key of their theory. It's sort of the one of the central ideas. So why theirs is more what we would call in statistics plateaukurtic, after a platypus's bill, fades out like this. I don't think it has anything to do with the magnetic cycle because they're not using that. Macintosh is. So, it's the distance between the two terminators prior to the cycle that is the key there. And I know that doesn't answer your question spot on. It's just because there's apples and oranges. The NASA NOAA panel is not using this model. We don't know what they're using.
Does the same apply to what the so-called double peak cycles?
Scott's been asked that, and I've been in the audience when that's the case. Now, here's where we can find the answer. I don't have the answer for you, but where we can find the answer is in this diagram. Is that there are several forces going on. Okay. And so what you see, some of these, like this is kind of a double peak. This is kind of a double peak. It's only a double peak if you smooth it so much it looks like a double peak. So let me beg the question of, is that important? Because remember, smooth sunspot cycle never affected your propagation. Or smooth sunspot number, I'm sorry, never affected your propagation. Only the actual sunspot cycle did. So to some degree, I'm not criticizing your question. I'm just saying that you see that little, what I call the cookie monster looking diagram. You only see that because we've smoothed it so much that that's for our consumption in data visualization. Does that make sense at all?
Yes, thank you.
Excuse me, Frank. I just want to jump in here really quickly. First of all, that was a fantastic presentation. I've already gotten some emails from people saying what a good job it was.
Well, thank you.
Thank you. Second, I would love to stay longer, but it's 5:30 here, and I have to pick up my son Anthony.
Yep.
So I need to run.
There.
Okay.
No problem.
I want to thank you, and I will be happy if you'd like. I can make you the host, and you guys can stand and chat as long as you like.
It's up to the group. If the group wants to chat, I can do it. My wife is holding her monthly book club meeting downstairs, so I'm not invited. So I got time on my hands.
I'll just turn it over to you, and anyone who wants to stay can stay. Anyone who doesn't, you're welcome to go. And we'll meet next week at the same time, and we will go right into the actual solar eclipse QSO party planning. So.
And the recording will go into your queue, right? When I end the thing.
Yes, when you end it, I will get an email saying the recording's available, and I will post it right onto the website. Super. And I will send an email out about it.
Go be a good father.
Thanks. Bye, everyone. 7-3.
Frank, this is Rich, K1HTV.
Okay. I'm sorry. There was two people talking. Who was?
Yeah, this is Rich, K1HTV, with a question about the double peak.
Yeah.
If it occurs, does it occur because the northern hemisphere of the sun is peaking before the southern, and they're not in sync? Is that why we may get two peaks? And I would guess the best hope is that they both peak at the same time. And as a result, again, you had even higher solar flux numbers, et cetera. Go ahead.
Well, like I said, I'm not a solar physicist, so let me give you my best guess at finding the answer. As I look, it's a replay, this little animation that Scott had prepared. You see some of those are sort of dual peaks. Now, I want to, and this illustrates what you're talking about, but what I want to do is go back to one of our diagrams that shows the smoothed versus the daily. And herein, I think, lies some answer to your question. I may have gone too far. I want to, and part of this is my background in doing work in data viz, including helping hire people in our computer science department at Mississippi State in that area. Here's one. You see the upper panel of the sunspot number from Silso. You see the red line is the smoothed. All right, you see this one, how you got the double peak, and that one you got a double peak, and there's the Cookie Monster with the double peak. That is a fabrication of the analyst. That never occurred in nature. That's not real. That is our smoothing of so many data points in a line, okay, to keep it from jumping around. Look at what actually happens, what we might call in nature. That's the black lines. So you see when you've got a double peaked, that's the smooth, but look at the real, the black ones are the actual sunspots. That smooth is an aberration probably of the difference between this high one and that low one that got added together and then divided, which is kind of how smoothing works. And the smoothing factor is how many of these do you put together? And when I talk statistics, I would show this to where you can smooth variation out of a data series so nothing happens. So I appreciate your question, but I think we have become so imbued with the smooth sunspot curve that we believe that is real. And what is real are the actual sunspot numbers. So you have a good question. It may be based upon a false premise, maybe, that it's the illusion that we believe that is real. I guess it's like the pictures of the hamburgers at Burger King or McDonald's. They really look good, but in reality, they may not look quite that nice. I don't know if that helps answer or not. It's easy to kind of get into that. And Scott's been asked this question, but let me say this. Back I don't know, back in the 50s or 60s, it's cited in the paper, the Radcom paper. A man named Wilson had proposed some of these ideas, but the data were not available at the resolution to separate the northern and southern hemispheres. And so they were always combining them. So you got a mashup. Let me get over here to where we have them. You had these red and blue lines, you didn't see those. You only saw the total, and they did the mashup to kind of get the idea. And it's part of what's changed things is the computing power and the flood of data. And then Scott's team had to go back to the far back as they could go to document their data. So it wasn't a fluke, as the reviewers had stated. So
well, you can see in the second, the half of the right side on the second box down, where one cycle, the red is peaking.
Here.
And then the next cycle, the blue is peaking. That's why I asked the question.
Rich, you may be correct. And I'm going to make a note of that. And Scott and I will talk, and he can educate me further. I've spent about 2 years studying at the feet of Scott. And I will say, I got him to agree in the interview that if his team is proven right, he's from Scotland. He's going to try to fit into his kilts and do a Scottish jig for me in a Colorado meadow. He's backing away from that promise. I can tell a little bit now because it's becoming more real. You have a great question, and I see exactly what you're getting at. And that would be worth looking at.
Thank you, Frank.
Yeah.
Frank, N0AX, I have a question.
Hey,
Is that me?
I said, hey, yeah, that's you.
Oh, okay, fine, thanks. First of all, I don't know who the editor was of the 1940 handbook, and it's not recorded that I know of. Who wrote what? And these typically come from whoever's handy and seems to know something around HQ as to who gets tabbed with writing stuff. But Handy wrote the first batch of handbooks, and then Warner was the editor, or at least the overseer of the handbooks in the 1940s. So probably Warner or somebody close to Warner wrote that material on the 11 or 22 year cycle, and clearly had been exposed to Hale's data back in the the teens and the 20s. So that's probably where that came from, but I can't really document.
Ward, thank you for that, because as somebody who's done a little history of science work, I thought that, and that's one of the reasons why I included that first article by George Hale. And if you think about it, when you're in a customer area, we amateurs are customers of the electronics world, of astrophysics, of some others. We blend a bunch of stuff. So I can imagine what you just said, that the editors of the handbook would say, that guy at Wilson Observatory, he's got some stuff laid out here that we need to think about. And he's talking about 11 and maybe 22, and he was trying to figure out, and his actual initial hypotheses about the sunspot cycle and the Hale cycle, he actually had it backwards the way it turned out, and he was surprised. What I love, Ward, about reading earlier periods of science is how much more humble scientists were, and if they got it wrong, they just flat said, I got this wrong.
Well, you can't do that today.
Yeah, no, it's hard, because having been on panels and having gotten millions and millions of dollars in my career, you can't admit your weaknesses or you don't get funded. So.
Yeah, well, if you go back and I wrote an article about where does the 468 come from.
Yeah, I remember that.
That was a really great detective story, and it came back from some really arbitrary measurements back in the early 20s. But at any rate, to address the questions here on the cycle, I think there's been a lot of numerology, creative numerology. Back
That's a great concept.
Can
I add something to this, Frank?
Sure.
Back in the 60s, I was a member of the Connecticut Wireless Club, and I met Ed Handy. He was actually one of the club members. In 1939, Ed Tilton, W1HDQ, joined the league, probably a little bit before that. And in 1939, he started the VHF column. I would not be surprised if Ed Tilton was the originator of that idea of the 22-year cycle and was responsible for it being in those early handbooks.
Rich, thank you. And let me dovetail back to Ward. Ward, I'm going to go back in my historical collection and try to read some of that to see if some of that was in a column, because correct me if I'm wrong, but that would have been kind of a thing that an editor of the handbook would do, is if in QST or some other places, there was some stuff that was, we might call it found science. That is, here's some new stuff. Here's one of our columnists writing about it. And that may have been where the editor for those years got it. Does that make sense?
Well, as the editor, I can tell you that goes on today. And we've just revamped the entire propagation chapter in a huge way. Carl was intimately involved with that, as a couple of other ham-sci folks were as well. So yeah, that's the detective of where does this come from. It's just that there isn't sufficient documentation of the old books. Anyway, to get to the present day, I think as we get a better idea of the physics of what's going on, that's where I've had trouble with the with the general prediction science is it's like, okay, you've got numbers here, but what's the physics? What's going on that generates these numbers? And only recently have we really gotten to the point where we can see these different cycles coming and going. And so to me, what it looks like is we've got a semi-chaotic relaxation oscillator kind of a mechanism in the sun. And what we're really after, you had that figure showing the essentially a phase space diagram of the length of time between cycles, showing, determining or affecting the peak of the following cycle.
Right.
And what you're after there is the strange attractor that this chaotic system is following, and it's going to rattle around it's going to be noisy. It's going to be jumping back and forth. And so what you're looking for is the attractor in that phase space that results in the relaxation oscillator of these bands coming down and then going back up and then coming down. So what's really going on under there? And as we find out more about that, I think we'll get a much better idea of what the cycle is all about. So from my point of view, it just as an interested observer and not as a solar physicist by any means, when we get a model that predicts at least 2 sunspot cycles and reasonably well, then I think we'll be on to something. And then we'll refine it over time. We'll understand more and more about this process in the sun and start to see things like these. Why are the phases slightly different? How can we tell about that and all that? That's out there a ways. But when we get a model that can do 2 or more cycles, then I think we've really got it.
Or you make some good comments. One of the things about chaos theory is there's some assumptions there, and that's what I've focused on as a statistician with some of the models that the panel uses. They don't tell us, we don't see them. So you're using like the mode to describe a whole distribution of thoughts, and that's a metaphor, not a statistical thing. One of the things I just finished reviewing a paper that will be submitted on the Terminator, and I'm sure it'll be published. But that little slide where I talked about, I made the joke about rasters faster, but vectors corrector, about not having to process all the bright point data, which is voluminous to say the least, but having a pretty good robust predictor of, let's go back and see when these terminators occurred, using backcasting, basically going back in the data, we can do what you're talking about. Now, obviously, anybody that knows their salt with regard to forecasting knows that backcasting is not always the same as forecasting. So your point's well taken, not arguing with the point, but I think a lot of the things that people, that's why we had these 61 models. People have dragged up everything they can come up with and not have much of a theoretical basis for them. I think that's what Rachel Howe was saying. Not much physics, and the statistics ain't much either. So that's what has happened. But I try to point out, and my friend Carl, I think, has sort of agreed that it isn't just about having more and more sunspot data. What causes sunspots? And that's where we need to think. And I think that's what Scott's team is doing. I think if you have time, I know you're real busy, but reading some of the works that Scott and his team have published gets you to the physics. Now, I pointed out, we don't get to go and stick our head inside the sun. Now, the Parker probe is going to give us more information than perhaps we ever had. That's why I put that picture in there. It's the only picture we have to date, the closest one to the sun, that we have. So your points are well taken. We tend to throw methods up without theory, and that's where I think we've probably been hurt for the most part. I'm just curious as to why that 22-year thing, Rich, entered there, the handbook on for a couple of years. They may have changed editors. Who knows? But I just found that oddly interesting, just that it was there and it coincided with Hale stuff. And then that got lost. That is not unusual. A number of paradigmatic changes in different fields of science occur because of the rediscovery of lost stuff, whether just ideas, data. And I think Scott and his team, and it was his mentor suggestion, hey, you might want to look at this. I think the Hale cycle may have some stuff there. Later, his mentor said, how the hell did we miss this? Anyway, Ward, I don't know if I addressed what you had to say or not, but that's just some thoughts on my end. Any other questions?
Hello, JWB at SBI has one.
Hey, Jay, go ahead.
Thank you for a wonderful talk. Really, really interesting. Have you done any coordination or contact with Dr. Tamika Scove, Whiskey X-Ray 6, Sierra Whiskey, the space weather woman?
I know Tamitha's work very well, but no, I haven't. Now, Scott knows Tamitha. He thinks she's a polymath and can do just about anything. Have not talked with her personally.
Oh, yeah, I met her at the last Ham Science Conference. She's a really nice person.
Yeah.
And I've got a feeling that it's my opinion that if you two could somehow coordinate on anything, the results would only be positive.
Yeah, look, I agree with you. Just a backdraw. I've had for the last 2.5 months, I've been in severe pain with a severely ruptured disc, and I've been physical therapy for 2 months. And I got kind of an amazing report yesterday from my neurosurgeon that my body has been absorbing the equivalent of the bits of your blown out tire that go out on the highway. It's been absorbing the cartilage that C7 T1, it just erupted. And he said, it's extraordinary how far you've come. I wound up in an emergency room at midnight, writhing in pain. And they gave me morphine to bring the pain. So honestly, your idea is a great one. I haven't been in a position to do much as far as do that, but that's a great suggestion. I'll try to follow up.
Yeah,
maybe she'll see
also
this. Maybe she'll see this on HamSci and express interest. I know she's busy too, but yeah, I agree with you.
Yeah. Also, and I'm as someone who has his own share of medical problems, you have sympathy, brother. But I would also ask if, in an understanding of the limitations of your medical problems, if it's at all possible, and I put this up in the chat, for you to present at the upcoming Digital Communications Conference, and then also later in October at the AMSAT conference. And if you can't make them, to please try and get on to speak at the next year's Ham Science Conference. I think
thank
that
you. Very kind of you to suggest that. And I'm a life member of AMSAT, but have not attended. And my health situation is kind of a wait and see. It ain't broke. He's not going to operate on it. So I'm hopeful that I can, be more mobile, and I'm feeling better, to be honest, feeling a lot better. So those are great suggestions. I don't know if they have people in by Zoom. That would facilitate the heck.
They can do that.
Yeah,
they can do that.
I'd be more than happy to do that. So if I don't know who the program folks are.
Okay. For the Ham Sci and for the Ham Sci.
Nathaniel asked me last year, and to be honest with you, I'm doing some work on Whisper and a different way of looking at what a circuit is as measured by Whisper. And I've been off. If you've seen any of my stuff on working with Rob Sherwood on receive test, he and I now are doing transmit phase quality, and I've been trying to finish some of that. He told me, look, shut up until you're over your neurosurgeon.
Yeah,
you don't need to be doing this. So I've had several balls, but I'm happy to share what ignorance that I have with other people. So
yeah, for Ham Sci, Nathaniel would be the right contact. For AMSAT, just for future reference, I would suggest the AMSAT just contact the president of the AMSAT and he'll
Been
point you in the
trying to
right
get an
direction.
interview with him. He does taxes and he begged off due to tax. I've been trying to do an interview for the ICQ podcast, but
Yeah.
I'll find a way to mention that. I appreciate that very much.
Yeah, and Tapper, same thing. Just go to their website, contact the organization, and they'll work you in.
Yeah, I
But
appreciate
good
that.
luck. But again, thank you very much. Speaking as the engineer that I am, great guy. In the Almighty we trust. All others must show your lab report with data, and you got data. You're
Whoever is a
good.
NASA NOAA panel that you need to share that with.
Take care.
Anyone else?
BE6XTC?
Yes, sir, Bruce.
Yeah, I'm just curious. Isn't it like trying to predict election polls with trying to predict solar spots and propagation in the future?
Having done those for the National Associated Press and having built 2 survey research centers in my career at Mississippi State, I can tell you they are quite different. The fundamental difference there is you're not predicting who's going to win. You're simply telling folks who likely voters are saying, and don't ever confuse a likely voter with someone who cast a ballot. I say that a little bit snarkishly at my own survey thing. I have a chapter in the handbook of survey research, but if you're saying you can't do it, then we should probably stop a lot of things that we can't do and just don't try. So I think if you look at that Helio forecast website that's cited in the article and I had on the slides, and as I put out on Twitter at the beginning of August, they're right on to the bone. I mean, their forecast, the actual reported smooth sunspot number was exactly what they predicted for that month. Now, that doesn't prove a darn thing, except they are a heck of a lot closer to what we've observed thus far than are the official predictions. So if your standard is to predict them perfectly, then, you know, that mean square error in the prediction model is never going to be 0. You're never going to get it exactly there. Ward made some comments about chaotic theory and some of those things. And at what point are some of the causes purely random? We don't know enough about the sun to know that. Some of those models assume things about the sun, and we don't know that. So, you know, I don't know. Do you think it's just an impossible task? Is that where your question's coming from, or?
Well, I don't think it's impossible. I'm just wondering, like, are we putting too much weight on predicting what's going to happen with the sun and with solar flux and all that fun stuff?
Well, if you are saying, are we putting too much on what the sunspot cycles do and relative to will we make a contact where we want to? Heck yeah, I agree with you, because there is a huge gap between whatever, particularly a smooth sunspot, as you've heard me go on at length for a moment here, the actual sunspot may govern it. But there's a whole lot more going on in that successful circuit from transmitter to receiver, right? I mean, we know that. So I agree with you. This should not be whether or not you're going to make a contact in the contest or de-expedition or just some friend you've got, you know, on the other side of the world that you like to talk to. You know, there's just a whole lot more to it than that. Just like I think Rob Sherwood will tell you, don't pick your radio based on what's ranked number 1. Any of the top 10 on my list will be good. Think about what else on that radio you think is good to gauge that. And I've tried to add to that with my composite Sherwood performance index. But yeah, I mean, do we say, give me a formula and I'll turn my radio on and boom, I got South Africa? Yeah, we tend to want to grab. I agree with you if that's where you're coming from. I agree with you a whole lot.
Yeah, well, one thing is for sure, I hope 25 is a really good time, because I would really like to get back into the radio hobby. I've been kind of off the air for a while, but I got to get my rig fixed and my antenna fixed up, and then, you know, hopefully I'll be able to get on the bands again.
Well, I hope you do. And it's Pete Giuliano, who's a part of the Solder Smoke podcast. Pete and I correspond, and he was banging me on the head about, you know, the bands are crap, all this stuff, this Macintosh stuff is no good. Well, you're looking at the smooth sunspots, Pete. Look at the actual ones as a better gauge of what's the fishing going to be like. There's a reason that bass fishermen want to know the temperature of the pond or lake they're fishing in at 4 a.m. because it's going to tell them how deep the bass are going to be for most of that day around the structure. That picture behind me, that's a real picture out my window. So the bass fishermen on that reservoir, they have some of the professional bass tournaments out there. I put out a proposal to the folks that run that thing. For a little bit of money, we can put sensors out there and we can know that 4 a.m. temperature at a certain height. Well, I'm not sure they want to do that. But there's a lot of stuff going into, you know, that connect. So I hope you get your stuff back on the air. Look, let's face it. I'm 69. This might be my last sunspot cycle. I hope not. But some of us in the baby boom generation, we've got some vested interest in cycle 25 and Macintosh's projections being good, because we may not be around for the next one.
A quick comment for Bruce. I would not wait till 25. Conditions right now are excellent. Today I worked into China, Indonesia, and Singapore on 17 meters. Conditions are great now. Don't wait another 2 years to get out, or 3 years to get on the air.
That's good. Yeah, I love 17. It's a really good band for me. For some reason, my G5RV always likes that one the best.
Yeah. Any other questions? Well, if not, listen, thank you. As I said at the outset, there are a few things that are more complimentary to be willing to sit through somebody talking for a couple of hours. And I thank you very much. I'm very touched by your questions and your comments and your encouragement. Scott and his team are continuing to work, and they've got more things coming out. So I see the day for the next cycle is we won't be looking at minimum or maximum. We're going to ask, where's the terminator? How far till the terminator? What's your prediction on the terminator? Because that will kick off that tsunami that we saw Dick Patty's simulation of. So we'll see where it comes out. They're willing to put their name and their data out there, and this website has got it there. A little different than Einstein and Newton, but the parallels are there too. So I'll cut it off if there are no more. And thank you very much. And we'll catch you next time. 7-3.
Thanks, Frank.
73. Thanks, Frank.
7-3.